Considering the levels of organization that are relevant to the human body, we want to start with the chemical level of organization, which would be the lowest or simplest level from which everything else is composed. Elements are the fundamental substances that make up everything around us. An element is a pure form of matter that cannot be created or broken down any further through normal chemical means. There are a lot of different elements. We'll look at a table of them organized in a periodic manner in a little bit. But this table shows us how our body is composed of some different elements. The outline silhouette of the human body there just shows how much of each of the main types of elements compose the body. They're not going to be in our body in a solitary mean. We don't have 65% of just plain oxygen in our body. It's going to be a component of larger molecules or compounds. The four that are listed here, the main ones, oxygen, carbon, hydrogen, and nitrogen, make up the four major elements of our body. And then the others making up the remainder fall into two groups: the minor elements, which would be pretty much the ones listed here other than those first four, and then the trace elements, which are collectively a very, very small percentage of what's in our body and are a number of different things that, if they were in greater quantities in our body, would probably be toxic to us. Atoms are the individual units that make up the elements in our bodies or in the environment around us. The word atom actually comes from the Greek word that means essentially cannot be cut, A being a negative prefix, and tome, T-O-M, being the root that means to cut. Before the actual nature of atoms was understood, this term was used in classical scientific literature as a presumed simplest state of matter. Now, of course, technology has gotten to the point where we can, in fact, cut atoms open, but the energy required to do that is quite extensive, and once we take an atom apart, the components inside of it do not retain any of the properties of that atom. An atom for gold and an atom for oxygen have properties of those elements, but the pieces inside, which are essentially the same sorts of particles, once they're removed from the atom, don't retain any of the properties of that element or the atom that they came from. Before we start talking about atoms, let me start by explaining the concept of a model. You're probably familiar with what models are, and if I just say the word model, I'm sure certain things come to mind. Maybe a child playing with plastic pieces that are being glued together and painted to represent, I don't know, a fighter jet or something to that effect. But models, in a more general sense, are representations that we use to understand something that's more complex. Now, the toy model is a representation. It's not an actual fighter jet. It's just a representation of it that the child can play with. And we use models all the time. In fact, it's really an integral part of how our brain interacts with the world around us. Think about what it takes for you to get from home to school. Now, that statement right there is very general and applies to each and every person listening to this presentation separately. But for you listening to this individually, when I said that, immediately your brain imagined what it takes to get from home to school, what it takes to get out of the house, get into your car if you drive to school, the route that you're going to take from your house to school, where you need to park around the campus, how to get from the campus probably to the classroom for this class, as you're thinking about it in the context of this material. That's all a model that's inside your head that you keep an idea of how to get to school. It's a simplified representation so that you can deal with it. You couldn't actually fit all of the space between your house and the school in your head with all of its detail, but only the important information is there in your model of that. This is a picture of a map, which is another type of model. This is trying to model what all of the land masses of the Earth look like. Now, the planet, of course, is three-dimensional and spherical, and it's just impossible for you to have a view of all of the land masses at once from one vantage point. You'd only be able to see the surface of the globe that's closest to you, but to be able to see all of them together, they're laid out in this two-dimensional representation. The projection of those land masses onto this sort of elongated circle, if you will, is taking some liberties with the actual dimensions of those land masses. And if you're at all interested in that, it's certainly a topic that the internet will go into quite a bit, talking about the different types of projections used on maps. Nonetheless, it's simplifying the information so that you can see it. Now, in this particular map that I happened to pull off of the internet, it represents a little bit more than just where the land masses are. You can also see that there's some texture to the geography. For instance, you can see where the Rocky Mountains go through North America, or the Himalayas go through Asia, to represent the texture of the planet at those locations. Again, it's a model to represent things a little bit more easily so that we can understand what we're looking at and make use of it. So back to thinking about atoms. Atoms are very, very small, and they don't really exist in a singular form. We don't look at a single atom. We have to look at a bunch of them together in a form of some substance. If it's a piece of gold foil or a jar of pure oxygen, something like that, there's not going to be a single atom there. It's going to be a whole bunch of them. So again, using models makes it possible for us to consider what an atom is. And the models that we use here are reduced down to what we need to use for this class. Now, there are two models represented in the atoms here, but they're both a little bit simplified for the purposes that they need to be used. The two models represented here are referred to as the planetary model or the electron cloud model, both of which were developed out of an early understanding of atoms. Originally, matter was thought to just be a homogeneous field of stuff, and as scientists started to get more understanding of what made that stuff up, atoms started to be modeled in a little bit more precise way, One thing that was clear from early experiments, and a scientist named Rutherford was instrumental in this, was that the atom actually has different particles within it. There's obviously a very dense central part called the nucleus, and then there were some other things outside of that that were less dense. The planetary model represents electrons orbiting around the nucleus like planets orbiting around the sun. The electron cloud model represents electrons being found within some space like a cloud around the nucleus. Now, both of these have some shortcomings, and if you were to go to a chemist and ask how they model what a atom looks like, neither of these really do justice to what chemistry really is interested in. But for the sake of what we're talking about today, understanding how atoms and elements and molecules are important for anatomy and physiology, these will suffice. And really the planetary model, which is maybe a simpler and older version of the model of an atom, is the one that we're going to stick with for the most part. And it'll suit our purposes. It does not suit a chemist's purpose by any stretch of the imagination, but it does address what we need to understand. These three models of different types of atoms are useful to explain what's found inside the nucleus. Now, all three of these atoms are a form of hydrogen, the simplest element we have as far as atomic structure. The first one that we see here, labeled protium, is the most common type of hydrogen atom. In the nucleus, it only has a proton, a positively charged particle. In the surrounding orbital, the circle representing the orbit of an electron, you see one electron there. That's basically what hydrogen is. The second one is a slightly heavier version of hydrogen, referred to as deuterium. It has a proton and an electron, just like the more normal type of hydrogen, but it also has a neutron, another type of nuclear particle, which has no charge. It just gives the nucleus some added weight as far as we're concerned. The third type here, tritium, is yet a heavier version of hydrogen. And in this type, a second neutron is found in the nucleus. Now, I want to make sure you understand the color scheme here is not labeling the different types of particles. If we follow the progression, the green one in the nucleus is the proton. The purple one that's added in deuterium and is still present in tritium is a neutron. The yellow one that's added in tritium is a second neutron. So don't think there's three types of nuclear particles. There's just two. There's protons and neutrons. And in hydrogen, the most abundant form of hydrogen by far, what's called protium here, there's just the one proton and electron, single electron orbiting it. Speaking of electron, now we have models of a few different types of elements. The first one is the same hydrogen. In all of these, the nucleus is simply represented by a circle shaded to look like a sphere with the abbreviation for that element in it. So H for hydrogen, He for helium, C for carbon, Ne for neon, without considering what's present in the nucleus. For hydrogen, it's most likely going to be that single proton that we saw just a second ago. For helium, it's going to be two protons and probably two neutrons. For carbon, it's going to be 6 protons and probably 6 neutrons. For neon, it's going to be 10 protons and probably 10 neutrons too. The fact that neutrons are usually the same number as protons is just common for most elements, atoms. There is some variation, but that's really nothing that we need to worry about in this course. We're going to concentrate more just on the electrons in the orbital shells, and the number of protons is really definitive of what element each atom comes from based on its atomic number. So, what we see here are electrons orbiting the nucleus in these electron shells, the planetary orbit model that we're talking about here. The first shell that we see going around, and the only shell going around hydrogen or helium, and the first shell around carbon or neon, can have up to 2 electrons in it. Then it's considered a full shell. Usually the number of electrons and protons is balanced. Electrons and protons have opposing charges, so they cancel each other out as far as the charge is concerned. So hydrogen with a single electron is going to have a neutral charge. Helium with 2 electrons will have a neutral charge. Carbon with 6 electrons or neon with 10 electrons will have neutral charges each their own. The electrons are going to be found in different shells orbiting around the nucleus. When we move beyond hydrogen or helium, where we're going to have more electrons present because there are more protons present, what we'll see is additional shells, additional orbits being added in. So in carbon we see the innermost shell full with 2 electrons, and then the next shell out is going to hold a remaining 4 electrons. And then neon we see that the first shell is full with 2, and then the second shell we can get the additional 8 electrons in. Now, for neon, this is going to be a full shell. That outer shell can hold up to 8. For the elements that we're concerned with, shells can basically hold this many. The innermost shell of any atom can hold up to 2 electrons and no more. Any subsequent shells that we're interested in can hold up to 8 electrons and no more. So if we go beyond neon, which has 10 protons and 10 electrons, we wanted to consider an element that had more protons. The next one along with 11 protons would be sodium. It's going to have 11 electrons if it's in its balanced neutral charge state, and we'd see an inner shell with 2 electrons, a second shell with 8 electrons, and then we need a third shell with 1 more electron outside of that. For whatever configuration we're talking about here in atoms, the outermost shell is also known as the valence shell, which is important in how atoms interact with each other. The valence shell, as far as we're concerned in this course, is always trying to get 8 electrons in it to be full. And sometimes when the valence shell has very few electrons in it, it can lose those electrons and go back down to the next most outer shell, I suppose you'd call it. So for that sodium ion I just described, if it loses that 1 electron in its outer valence shell, that shell's gone because there's nothing in it, and so its outer valence shell is now similar to what we see in neon here. It's just a second shell with 8 electrons in it, which happens to be full.